All right, we are continuing on here, still chapter 14, still rolling through it here. Last time we got into obviously salts, and we salted this morning as well. And again, our salts, remember that when we look at it, we want to really determine, will it go through hydrolysis? And pretty much if any part of the salt comes from anything weak, either an acid or a base, you will get hydrolysis to occur, as it's going to be relatively strong. And really, again, it's going to be that salt that will react with the water and will either produce hydroxide when it sort of gives away the H plus the water, or if the salt reacts with water, it can accept the H plus and produce H3O plus, which obviously would be acidic. And as we talked about a number of times up to this point, this is really how we can recognize, which K value that we should be using based on what is formed there on the product side. And as we talked about last time, as we did this morning as well for lab, again, in certain cases, especially when you have a salt that comes from a diprotic acid or a triprotic acid and is amphoteric and can go both ways, that is where we do want to oftentimes compare the Ka to the Kb value. And whichever one is larger should be what should happen in that case. And as we talked about in a little bit more detail this morning as well, you want to make sure, again, you're comparing the correct Ka and the Kb value based on the dissociation of that diprotic acid. Also, we use the comparison of the Ka and Kb values in a situation where both parts of the salt could hypothetically go through hydrolysis. For example, we looked at just on that table, something like this. Again, in this case, both parts of the salt come from basically weak things, and they both can go through hydrolysis. Here, we would also look at the Ka and the Kb value for the positive guy and the negative guy and compare it, and whichever one's larger would obviously be what it would go through. We to calculate the pH, it is going to be an ice table like normal. Again, the difference here, a couple things you do need to watch out for when you do solve for H plus or the X, that will equal the OH minus when you're doing a Kb type calculation. And obviously that will be the H plus in a Ka situation. I guess I should write the right letter next to that. That would be a Ka as well. I'm just gonna go with different letters, KZ. No, I don't know what that means. So, and obviously you want to make sure that you are using the correct Ka or Kb when you do that. And that is where our Kw comes into play. A times Kb in that case. And when you are choosing, as we talked about this morning, technically speaking, when you add up your Ka equation that you would get from the table and your Kb hydrolysis one, for example, you should, as I did earlier today, end up with water at the end, right? And they should cancel out completely. And then that's the way you can kind of check yourself to make sure you did grab sort of the right values. Any questions on any of that stuff there that we're doing today? All right, continuing on halfway through-ish, chapter 14. These are oxides. Oxides are obviously things that do contain oxygen. They're sort of forerunners to both bases and acids. And our group 1 and group 2 on the periodic table are what are referred to as being basic oxides. Because frankly, if you add a little bit of water to any of those guys, you're going to kind of generate some sodium hydroxide, magnesium hydroxide, calcium hydroxide. So you're going to get a lot of those bases that are going to be generated. Over here in our nonmetal region here, we got some acidic oxides, which means if you add some water, for example, to CO2, you get a little carbonic acid happening here. And those are why there are acidic oxides. We have some that are amphoteric, so like our beryllium coming through here. Those guys can go both ways. Again, amphoteric means that they can either be an acid or a base in that situation. It kind of depends on the situation. So up at this point, we talked about a couple of definitions of an acid and base. So the basic definition of an acid is something that's able to produce H plus or H3O plus in solution. The Bronsted-Lowry definition of an acid and a base. Again, an acid is a proton donor, which is a very common definition that we use a lot. Obviously, our base is a proton acceptor. So to add to our list here, we have another definition of an acid and base, and this is what is referred to as a Lewis acid and base, and that is our same friend Lewis that we think of when we draw his structures. Yes, so Lewis structures. So when we draw Lewis structures, that involves electrons. So not a big jump here that the definition of a Lewis acid or base actually involves electrons. So it does not involve protons. So the definition of a Lewis acid is something that will accept a pair of electrons. And something that's a Lewis base will actually donate a pair of electrons. So it is opposite of Bronsted-Lowry in terms of what is accepting and what is being donated. And we're also talking about electrons here. So for example, in order for something to be able to donate a pair of electrons, they typically a lot of times are things that are polar and have a unpaired electron pair there. There are also things that are negatively charged ions. They actually are negatively charged because they have extra electrons, right? So they have them to donate. So usually things that are really good Lewis bases, which we'll see in a later chapter, which deals with transition metals and complex ions. These are things that have, sort of a polar molecule that has some unpaired electrons, like water also is a Lewis base, and things that are negatively charged that have those extra ones. Things that are Lewis acids are things that accept electrons, and things that are most likely to accept electrons are things that are electron deficient. So they're missing some electrons, right? And that allows them to have positive charges, right? And be able to accept those electrons. So as we look here, for example, water and our ammonia, in this case, this guy is H+, he is missing electrons. The hydroxide is going to be able to donate over the electrons and make our water in this particular case. Here, the H+ is deficient. Our ammonia, which is polar, has those pair of electrons that can donate over. So this is actually a Lewis base, and this would be our Lewis acid. It is the same idea of what we were talking about earlier with why copper, for example, has a +2 charge, can able to complex ion with water, right? Water is polar, it's got these electrons. This guy's +2, which means he's electron deficient. That is how they can interact with each other. So when we look at that little guy that I wrote on the board, and it's the copper with the 6 waters or 4 waters around it, it's really a Lewis acid base sort of situation that's happening. It's those water kind of giving those electrons over to the electron deficient metal that's going to allow them to sort of interact with each other. We could also use our same definition of Bronsted-Lowry in certain situations. Because we do have an H+, we could do it in the opposite direction here, and that would be a Bronsted-Lowry acid, and that would be our base, and that is still our Lewis base and our Lewis acid. So if you do have an H+ involved in a reaction, you can still roll with the Bronsted-Lowry definition, and you'll be able to figure out what's the acid and what's the base. But you could also look at it as a Lewis acid and Lewis base. Lewis bases are really important in terms of transition metals and complex ions. They are what are sometimes referred to as ligands. These are things that attach. Same thing with boron. As you may remember, speaking of bonding, boron is an exception to the octet rule. It's an incomplete octet. It means it has less than 8 electrons around it. And because of that, it is also very much electron deficient, right? So it's going to be able to accept those pair of electrons from the NH3, and again, making this our Lewis base and this our Lewis acid in this particular case. Now, when we look at this here in this particular example, there's actually no hydrogen being transferred here. So a Lewis acid and base sort of definition is one that you can apply to a lot of things, even when you don't have that proton being transferred. So you can still kind of use the Lewis acid base definition to describe what is happening. Any questions on Lewis acids and bases? All right. So the last part here for our first half of this series of chemistry is we're going to talk about diprotic acids and how we do some calculations with diprotic acids. So obviously we have multiple types of acids that we could have. We have like HA, which is a monoprotic acid, which means again it has that one H plus that it could give. We have something like H2A, like sulfuric acid, which is a diprotic acid, which has obviously two hydrogens that can come off. Something like phosphoric acid is a triprotic acid, and obviously again that has three that comes off. So as we've been talking about, each of those hydrogens do come off one at a time, and we will have a Ka value for each of those that come off. So again, if we look at our phosphoric acid, that very first step is going to be that H plus that comes off, and we'll be left with H2PO4 minus. And that would be the Ka1 value that we see in that table, and we'll go with 7.5 times 10 to the minus 3. The next thing that happens is that H2PO4 minus will come off. One more hydrogen from it. And that's going to make our HPO4 2 minus. That's going to come off there on the product side. That's going to be our Ka2, which looks like 6.2 to the minus 8. And the last step in this process is this guy here will basically get rid of its last hydrogen and make a little phosphate in this case, giving us our Ka3 of 4.8 to the minus 13, looks like. So again, this is a stepwise fashion, although sometimes we think about the overall sort of reaction that's happening. And if you went through here, I'm not going to cross them all out, but I'll just kind of dot them. These guys cancel, and we get basically overall what's happening is our H3PO4 is going to basically dump off 3 hydrogens and be left with phosphate as this cancels out as well. So it's got phosphate. So sometimes we get the wrong impression that, you know, they all pop off all at once, because we always will probably see up until this point just like the overall reaction that's sort of happening. But again, it is a stepwise process. So a couple of things. First off, when we look at this, or if you look and compare any of these diprotic acids, and by the way, there's our sulfuric acid, and that's usually what you'll find on the table, which is not very helpful for calculations, which is just a large value. And that's really because the second one that comes off there is more of a weak acid, and sulfuric acid with the first hydrogen is more of a strong acid. Is it easier to take off the first hydrogen or the last hydrogen? Which one's easier? The first one is easier, then the second one gets harder, and the third one gets even harder for the hydrogen to come off. Again, at the very beginning there, you have something that's neutral, right? So you take off something that's positively charged, which means now it has a negative charge. So to get rid of something that's positively charged, a little bit harder to remove that. When you get rid of that second hydrogen, you now have something that has a -2 charge, even bigger negative charge, right? So it's going to be even harder to remove that H plus from it. And we see that actually in the numbers. When we look at the numbers, the Ka1 value is to the -3, which is a larger number, right, than when we get to our second Ka value, which is to the -8, and even larger there than our third one, which is to the -13. The Ka value, as you go from the first one to the second to the third, gets smaller. And when I have a smaller K value, that means I have more or less products. I'm going to re-say that question one more time, I think. So when I have a smaller K value, do I have more or less products? Less. I know. So I asked a weirder question. I understand. As I know, it's like a double negative. Yes. So I'll say it like we usually do. So when we have a small K value, we mainly have reactants, right? Not so much products. Is that better? All right, I'll try not to mix up the sentences here. Let's change it. So because we have a much smaller one, that means we have less of the products on this side. And if we have less of the products on this side, that means we have less H pluses come off at that point, right? So we have more of the guys staying together, less of the H plus coming off, as we do at the beginning there. All right, and we do see that trend as you look at all these Ka1s to Ka2 values. You should see that the second Ka value should be smaller than the first, as it again gets harder for it to come off. All right, so let's take a look actually at a problem. We'll come back to this in just a second here. All right, we want to do this problem where we are starting with 5 molar phosphoric acid, and we want to basically figure out everybody's concentration that's in the ballpark here in the beaker. So we have our 3 Ka values. Again, they basically represent each of those equations that we just saw, where each of them are basically losing a hydrogen. Obviously, each of these go to each of these guys here. All right, so in this case, we're looking for the pH. We're also looking for basically everybody else's concentrations. So the first thing that's going to happen in this problem is we're going to have really the first dissociation happen. So let's take a look at the calculation for that. And maybe I get to go here. Come on. So we have our H3PO4. Going to break apart into our H plus and our H2PO4 minus. And that's going to be our Ka1, and that is our 7.5 to the minus 3. All right, so in this case, we are starting with 5 molar of our phosphoric acid. Clear, we're going to do an ice table as this is a weak acid. So we're going to have our 0 and 0. Our change here will be minus x, plus x, plus x. It's Thursday, I'm sorry. All right. It's been a long day. All right. All right, so at the end here, we do have 5 minus x, x, and x. Any questions on the ice table there? This, again, is just like a normal ice table. Plus is on the right there. I got them there. And minus is on the left. This is going to go into our Ka1 expression here, which is our H plus over times our H2PO4 minus. Our H3PO4, and that's going to equal our Ka1, which is our 7.5 times 10 to the minus 3. Putting in our values at this point, this gives us x squared divided by 5 minus x is equal to 7.5 times 10 to the minus 3. That is technically a small value of k, so I'm going to try my assumption here and see how I do. So we're going to assume that x is equal to 0. And that would get me x squared divided by 5 equals 7.5 times 10 to the minus 3. We're going to multiply the 5 to the other side, and then I'm going to take the square root of it as well. So I'm going to multiply and then square root. So we're going to take 5 times 7.5 to the minus 3. A little square root action on it there. Going to give us an x value of, looks like 1.9. times 10 to the minus 1. And I do need to check that, right? So I'm going to check that by dividing it by what I was going to subtract it from, which in this case is 5, and times it by 100%. And we're going to see if we're in good shape here. And it looks like we're at like 3.87, which is in good shape. Happy face, and probably why I originally changed it to 5 from the original number, so I didn't have to do the quadratic. But you know, make sure you do check it. So since that obviously is a good check, we can use it for our table. So from the very first table here, we do have several pieces of information that we've answered. We definitely have this guy, which is what X equals. We also have the H plus concentration, which is what X equals. So at this point, we know that H plus also equals the H2PO4 minus, and that is a concentration of 1.9 times 10 to the minus 1 molar. We also have the phosphoric acid concentration at equilibrium from this table, and that would be the concentration of H3PO4 would equal 5 minus 1.9 times 10 to the minus 1, and that's going to give me 5 minus 1.9 to the minus 1. Looks like 4.81 molar. So from our very first sort of ice table here, we were really able to pick up a couple things we were looking for: this concentration, and the H plus concentration. Any questions on that so far? All right, but in this particular problem, they kind of want some others. They want this guy here and they want that guy. So the only place, or one of the only places we can see this guy is in the second reaction. So when the second H plus comes off, that is what's going to happen. So we need to go to the second step here. So we're going to take our, maybe we'll take something. Just going to keep writing lines on it. Maybe it'll go. There we go. There we go. We got our second dissociation, which is our H2PO4 minus and our H plus, and going to get a little HPO4 2 minus. And at this point, this is going to be our Ka2, which in this case, if we look back there, is 6.2 to the minus 8. So now when we do our ice table, do we have a concentration of this guy to begin with? We do, and it's actually the equilibrium concentration that we had from the previous table. And we also have some H plus that was there originally, right? Also from that very first dissociation that came off. So we do need to put those numbers into our table, and that's 1.9 to the minus 1. So we do have 1.9 times 10 to the minus 1. We also have the same thing here for this guy. So it is not 0 in this case, and this guy would be 0. So our initial line here is basically coming from our equilibrium line of the first table and the first dissociation. The rest of the table will be like normal. So we're going to go minus X and do plus X this time and plus X. Going to give me at equilibrium 1.9 times 10 to the minus 1 minus X. 1.9 times 10 to the minus 1. This is plus X, and that is X. Any question on the table there? This is going to go into our Ka2 expression, which is our H plus and our HPO4 2 minus divided by our H2PO4 minus. And that's going to equal 6.2 times 10 to the minus 8 in this case, right? All right, at this point, we're going to put our equilibrium line in like normal here. So we will not do that. So we will go with our 1.9 times 10 to the minus 1 plus X times X divided by our 1.9 times 10 to the minus 1 minus X equals 6.2 times 10 to the minus 8. Worked good the first time, so why not try it the second here? I'm going to assume that X is equal to 0 here, so that's even a smaller one. Can I get rid of all the X's in this case? Right, so in this case, it's only going to be the X's that we're adding and subtracting from. So when I do that, that reduces this down to 1.9 times 10 to the minus 1 times X divided by 1.9 times 10 to the minus 1 equals 6.2 times 10 to the minus 8. I think I could do that math. That's just going to cancel, basically. And that will give us an X value of 6.2 times 10 to the minus 8. Once again, here, we might want to check our assumptions. So we'll take that and divide it by 1.9 times 10 to the minus 1, times it by 100%. And I think we should be pretty good here. So we're going to have 6.2 to the minus 8 divided by 1.9 to the minus 1 times it by 100, and you're not even near 0.1%. So it's really, really small. So the check is good in this case. All right, so that means that this X value, if we go to our table, now gives us the concentration here of HPO4 2 minus, which would equal 6.2 times 10 to the minus 8 molar in this case. Yeah. What happens when I take my X value and put it back into each of these? Do the numbers change? They do not, because that's basically, I'm sorry, Liz, but it's 0.000006 or 62, right? And so it's a very, very small number. So even when you subtract it from the first number and add it to the other number, you're going to end up with the same number. So it doesn't really change. So they are still really that same concentration. Any questions on that there? All right. So now if we go back to our original question here, we just knocked off that guy there. So the last thing that we're kind of looking for in this case is what is the phosphate's concentration? And once again, unfortunately, the only place phosphate is found is in the third step here. So we do have to go to the third step in this case to get the phosphate, to figure out its concentration. So we're going to use our third dissociation there, which should be something like H2PO4 or not, HPO4 2 minus is kind of similar. I know that's what happens when you get a history major to teach you. All right, HPO4 2 minus. No. All right, so phosphate here is our third step, which is our Ka3. And I'm really old. What is that value there for Ka3? It is. Thank you. Okay, so we have our third Ka value here, but just like what we did on the second ice table here, we do have to perhaps come back to our table before, because we do now, right, have a concentration of this guy from the previous table, and we still have our kind of same concentration there of our hydrogen, as it really didn't change in that case. So we got 6.2 times 10 to the minus 8, 1.91 times 10 to the minus 1, I think. And this is 0. So we do have some numbers there. And once again, they're coming from the previous table that we just looked at. Our change is going to be minus X, and plus X. That means at equilibrium, we got 6.2 times 10 to the minus 8 minus X, 1.91 times 10 to the minus 1 plus X, and X. At this point, we're going to go into our Ka3 expression, which is our H plus and our PO4 3 minus divided by our HPO4 2 minus, going to equal our 4.8 times 10 to the minus 13. So popping in our numbers here, 1.91 times 10 to the minus 1 plus X times X divided by 6.2 times 10 to the minus 8 minus X equals 4.8 times 10 to the minus 13. We went 2 for 2 so far, so why stop now? We'll go assume X is equal to 0. And again here, that's again going to take out these two X's only, leaving the other one. And that will reduce this down to basically 1.91 times 10 to the minus 1 times X divided by 6.2 times 10 to the minus 8. And that will equal, I'm just going to steal the number right there, 4.8 times 10 to the minus 13. So now I'm going to multiply to this side, and then I'm going to also divide that guy next, right? So I'm going to do both of those. So taking our Ka3, which is 4.8 to the minus 13, divided by 1.91 to the minus 1, and then timesing 6.2 to the minus 8, doesn't matter which order you do it in. 1.6 is what you should get for that X. 1.6 times 10 to the minus 19 We are going to check it. You can divide it by either one. We'll do the 1.91 times 10 to the minus 1. And times it by 100. And again, you're nowhere even near 1%. So our check here is good for this one as well. So from our ice table here, that is the concentration here of phosphate, which is this number here, 1.6 times 10 to the minus 19 molar. Is that a lot of phosphate? It's not, right? Super small amount. Also, when we go back into each of these, will those numbers change? They will not, again, because it's a really small number. So this is sort of what we expect, as we were talking about, right? It gets much harder as you go from the first hydrogen to the second to the third. So by the time you get to third, not much of it's breaking apart, as we can definitely see by the phosphates concentration as well. We also see, as we go through each of these steps, the majority of all of the H plus came off in which step? The very first step, right? So again, as we saw here, you can put that number back in. It's basically the same number. You can put the number back into here. It's basically the same number as what we got on our very first step. So the take home of this story is, we do want to calculate the pH, by the way, right? So our pH in this case would be the minus the log of 1.9 times 10 to the minus 1. And that's going to give us a pH of about 0.72, I think, was pH. I feel like I added an extra 1 to that. I think it did matter here on the other ones. But the take-home message is here: if you're dealing with anything that is a diprotic or triprotic acid, and you're simply asked to calculate the pH of it, you pretty much could do the first step, and you probably will be okay in most cases and get the H plus concentration from the first table, and that will probably be the H plus concentration for the solution, and you'll get the right pH. If you have a problem like this one where it wants the concentrations of everybody, it may require you to go to each of those steps to find something like phosphate and what its concentration would be. But again, if you're just simply asked what is the pH of it, and it's a diprotic or triprotic acid, pretty much all of the H plus is going to come off in that first step, and you could use that usually to calculate the pH, and you'll be in good shape. Any questions on polyprotic acids, how to do them? Kind of the same step along the way. Just a few more extra H's to coming off. Yeah. Any questions? Good. All right. I feel like I'm out of slides. What? You do have a question? I'm sorry. Yeah. It does. So along the way here, I think only on the third step, I added an extra 1. I like the 1. I was trying to do it off my memory. It killed me, but I'd try to. But the reason is, if you take the X value at step number 2 that you got, and also step number 3, and you put it back into here, it's so small at each of those steps because not a lot of it is breaking apart. It's pretty much staying together after that first step. So after that first guy that releases the hydrogen, once you got the second and third step, not much of it's fallen apart at that point. So it's such a small number that basically the H plus concentration that you got after the first step is really the same amount of H plus that you have after the second step and the third step, because not a lot of it is coming off anymore. There is a smidge. I mean, I guess you could call 1.6 times 10 to the minus 19 something coming off, but it's very, very small amount of hydrogen coming off at that point. So the majority of it's going to jump off there in the first H plus. Yeah. Other questions? Yeah. All right. So that is part 1 of the journey. All right. Back 9 here of this chapter. This is where it's all going to come together for you. Buffers, titrations. Oh my. Yes. All right. All right. So we're going to talk about buffers. We're going to talk about titrations. This is definitely the heart of the class, where that conceptual and the calculation part need to come together for things to work correctly. So we're going to start with really buffers, and really the idea of what is known as the common ion effect. And the common ion effect is pretty much what the name implies. You have a ion that's in common with the stuff that's floating around in there. So for example, let me just use the most popular one known to man, which is acetic acid. So if I have a solution of acetic acid, which is a weak acid, it is going to break apart into acetate and a little H plus, right? Which means if I took my beaker level view of my beaker here, I got mainly acetic acid floating in there, but I do have some acetate, right? Gonna set up a nice little equilibrium, and I got some H plus basically floating around in the beaker that's happening at this point. Now, in this point, it's a weak acid, which means, you know, it's not going to completely dissociate. We're going to have back and forth in this equilibrium set up. Now, if I took this acetic acid and I also added into it some sodium acetate. So sodium acetate is a ionic compound. It is a strong electrolyte, which means when it goes for a swim, it is going to 100% break apart into sodium and acetate. So 100% here. It will not set up an equilibrium or anything like that because it will completely break apart. That means that essentially here, I'm going to be dropping into this beaker some sodium and some acetate. Yeah. The common ion here in this case is the acetate, right? And we see that in the only thing in the beaker that is set up in equilibrium, which is the acetic acid, right? So we're going to draw back to our friend Le Chatelier and his principle. And it says, if I add some more acetate to this, what's going to happen to the equilibrium? It is going to shift to the left, right? So when we have some more acetate in there, it's going to cause this equilibrium based on Le Chatelier's principle to shift to the left. That means when it shifts to the left, my acid is going to break apart more or stay together. It is going to stay together. And when it's going to stay together more, that means will I have more or less H plus in the solution? I will have less H plus in the solution, which means it's going to cause the concentration of my H plus in this case to go down. That's going to cause the pH to go. That is both options, but we'll go with the up option in this case. So it is going to cause it to go up, right? So the H plus and OH minus are tied to each other. So in this case, if we're starting to bring down the H plus, we are bringing up the OH minus, right? And we should start to see the pH be higher. And that's in comparison to what the pH would be with just acetic acid by itself. So acetic acid by itself would have a certain pH. We'll call it 4.74 perhaps. And if you add some sodium acetate to it, you would see the pH go up. Will it go all the way up to a basic pH? The answer is probably not, but it will probably be higher than the pH of acetic acid in comparison. So it's not going to jump all the way to basic, but it will be a higher pH than what we would see with acetic acid because there's actually less H plus in that solution because of the addition of the acetate. So this is the idea of a common ion. When you have a common ion present in a solution, what it does to both a weak acid and a weak base is it will suppress it from breaking apart. And basically that means that you will have less H plus that's free in the solution and less OH minus that's free in the solution. And both of those things will have an effect on your pH. As we know, right, the pH again is minus the log of the H plus. And that H plus is frankly the amount of H plus that is freely floating in that solution. So that's what has a big effect on it. And when we're talking about bases, it's the same idea. It's the amount of OH minus that is freely floating in that solution. And the more OH minus you have, again, the less H plus you have, and vice versa as they move opposites of each other. So these presence of these common ions will keep the weak acid and weak base together, not allowing them to release as much H plus or OH minus as they normally would if it wasn't there. And that's going to cause the pH really to sort of fluctuate. In the case of a weak base, it would prevent as much OH minus being there. So what would happen to the pH of a weak base when you have a common ion with a weak base? Should it go up or down? Yeah, the pH should go up or down. It should go down, right? And again, in the case of a weak base, by itself, you're going to have a certain amount of OH minus there, right? When you have a common ion with that weak base, that's going to cause less OH minus, right? So if we have less OH minus, we then should have a little bit more H plus, and a little bit more H plus to start to see the pH start to come down. Again, it probably won't drop to an acidic pH, but in comparison to the weak base by itself and the weak base, which is common ion, you will see that kind of difference in pH. Any questions on that there? And that's what we see down here, our little Le Chatelier's principle type of thing. Guy from the past there. So let's take a look at a problem here where we could kind of see this effect maybe happening. So why don't you do the first one here, which is part A, and see what you come up with. So don't worry about part B yet. So just do part A, which is calculate the pH of a solution that is 0.2 molar acetic acid. The Ka value for acetic acid is right there. So calculate the pH and see what you come up with. We're looking for the pH of 0.2 molar acetic acid by itself. I have a Ka value for acetic acid. So again, I do know that it is a weak acid, and that should scream to you ice table. So we're going to scream at our ice table here. That's acetic acid. Going to break apart into a little H plus and a little acetate there. And we got a Ka value 1.8 times 10 to the minus 5. We're going to do our ice table here. So we got 0.2 molar. We got nothing of anybody else. So there's going to be zeros. Change is going to be minus X plus X plus X. Going to lay us up here 0.2 minus X, X, and X. Any questions on the ice table there? All right, so this can go into our Ka expression, I think, which is very glary right now, H plus and acetate divided by our acetic acid. And that again is going to equal our 1.8 times 10 to the minus 5. Put in our numbers in, gives us X squared divided by 0.2 minus X equals 1.8 times 10 to the minus 5. Been having really good luck. Why not continue our streak here? Too late to buy the lottery ticket, apparently. Okay, so that is X is equal to 0. One person won. Is that what I heard? Wow, that's pretty good. I'm still here, so clearly I won. All right, so that X is going to be the one we're going to get rid of here. That's going to be X squared divided by 0.2 is equal to 1.8 times 10 to the minus 5. We're going to, again, multiply and take a little square root action of that there. And we're going to get 1.8 to the negative 5 times it by 0.2, square root it. Going to give us an X value of 0.00190. We're going to check it by dividing it by 0.2 and times it by 100%. And if we do that, I think we are okay. That's like a 0.9. So check is good in this case. So because check is good, that means if we're really interested in the pH, so that is what we're interested in here. And we can see at equilibrium, that equals X. That means that our H plus concentration equals X, which is 0.00190. And that would be molar. That could then go into our pH minus the log of 0.00190. And that's going to give us an opening pH here of about 272, 2.72 in this case. That is acidic, which is good since this is an acid. So that's a good move there, I think. Any questions on any of those stuff? This is really just a calculation we did at the beginning of that chapter, right? A Ka type calculation, just a weak acid, a little ice table, some X's and some pH's. Any questions on that? Okay, so now let's see about part B here together. So now we're going to look at the same acetic acid solution, but instead of it being by itself, we're also going to toss in there some sodium acetate at 0.3 molar. I was going to say percent. That didn't sound right. So we got our 0.2 molar acetic acid, and we're also going to combo it with 0.3 molar sodium acetate. All right, so in this case, we definitely have our weak acid, which is 1.8 times 10 to the minus 5, the Ka value for it. Our sodium acetate in this case is a strong electrolyte, and we have acetic acid. Will they both set up an equilibrium in solution? It will not. This is being a strong electrolyte will actually just break apart in solution. So really our sodium acetate in this case is a source of basically these two ions, right? The sodium ion and the acetate ion. And that means that really our calculation here is going to be based on the only one that's going to set up an equilibrium, which is our acetic acid in this case. And it will set up the same equilibrium as we saw previously. And now, as we saw earlier, our common ion in this case, right? We now have this common ion is going to be our acetate, right? So that is our common ion that's going to happen. And that's important because in this solution, the sodium ion would have a concentration of 0.3 molar, and so would the acetate, right? As it's a one-to-one relationship between the sodium acetate and the sodium acetate and the acetate. So how it breaks apart is a one-to-one relationship, and that gives us concentration. So now when I come to my ice table, 0.2 molar, right? This is going to be 0. Should I have a number here? I should. And it's because of the common ion effect. It's going to be that 0.3 molar that's going to be supplied by the sodium acetate. It's like you dumped in there some sodium acetate, you added some more acetate to it. If I do not put a number on the right-hand side of this ice table, what type of problem am I doing? Doing the exact same problem I just finished doing, right? So you're going to end up doing the exact same problem. So really important common ion problems, and these are, as we'll talk about in a second, these are really buffer problems as well, is people, when they go to do the ice table, they're not used to putting something on that right-hand side. And if you don't do that, then you're not really doing a common ion problem. You're just doing like a weak acid problem, and obviously you'll get the wrong answer. The rest of the ice table is going to be the same here. We're going to end up with minus x, plus x, and plus x. This is going to give us 0.2 minus x, and also something that people commonly will make a mistake on. This is plus x at this point, not minus x. So sometimes at this point we have a lot of minus x's happening, so we just automatically throw down the minus there. So you want to make sure that that is plus. Just like before, this is going to go into our Ka expression based off of acetic acid, because that's the thing setting up the equilibrium in this case. So we'll have our... Yeah. In this particular problem here? Yeah, we don't, because in this case, this is a kind of a separate situation, I guess, if that makes sense. These are both being kind of tossed in together at that point. So the first one with acetic acid by itself has come to equilibrium with that concentration. So this is assuming that you're kind of mixing them together to start with. So at the beginning, it hasn't come to equilibrium, so we don't really have that concentration. Yeah, so we kind of carry it over only in a situation where, you know, kind of similar to what we did with the diprotic acid, because in that sense, the diprotic acid or triprotic acid goes in for a swim, and really everybody's starting to break apart. You know, you got that floating around. So as it goes to technically the second step, when it occurs, they have some of that H plus already there. But here, it's everybody's kind of starting at the same point. Yeah. Other questions? Okay, so our Ka in this case, and again, we know it's a Ka because obviously it's an acid, but we do have the H plus. It's going to be our H plus, our acetate, divided by our acetic acid, and that's going to equal this number here, which you will commit to memory because it's the most common example. We use it like 5 million times before this semester's over. 1.8 times 10 to the minus 5. We're going to put our numbers in here, and this is going to give us x times 0.3 plus x divided by 0.2, let's see, minus x equals 1.8 times 10 to the minus 5. We're going to assume that x is equal to 0. Why not? We'll try to keep our streak going here of things working. So that's going to reduce this down to x times 0.3 divided by 0.2 is going to equal 1.8 times 10 to the minus 5. We're going to, again, multiply here, divide as well. And if we do that, we end up with 1.8 to the minus 5 times 0.2, a little dividing by 0.3, going to give us an x value of, I'll count the zeros, 1.2 times 10 to the 1, 2, 3, 4, minus 5, I think. We're going to check it by dividing by either one, really. We'll go 0.3. We're going to times it by 100, and we're like 0.004%. So the check is good in this case. Yeah. That is going to get us our H plus concentration, which in this case is going to be 1.2 times 10 to the minus 5, and that is what we need here for our pH. So our pH will be minus the log of 1.2 times 10 to the minus 5. That's a 4.92er there, I think, as well. Any questions on that calculation? No? So what did we see if we compare sort of the previous one to this one? We see the pH went up, yes. And we see the H plus concentration. The first one was 0.0019. H plus concentration. The second one is 0.000012. H plus concentration went down. pH went up, which is what we would expect to happen because of this common ion, causing the equilibrium to shift this way, causing less of this to come off. And that's what we see when we compare the two numbers and the pHs as well. Any questions on that there? No. All right. So continuing on then, I guess. So what we see in this problem and what we see in a lot of problems that have common ions, which are really buffer type problems, is if you start with the initial concentration that's relatively big, pretty much what you end up with and what you start with is basically the same concentration. So if we go back to the example we just did there, if I were to take my X value, technically speaking, and put it back into here and here, I'm going to end up with 0.2 and 0.3 still, basically. So because of that common ion and it keeping it from breaking apart, we're not going to get a big change. We're not going to get a big change in the initial concentrations. So the good news is when you have common ions that this happens in most cases, you can actually avoid the ice table. There's the happy words right there. And you can do a lot of things here. And you can use our friend, the Henderson Hasselbalch equation, or David Hasselhoff equation, whichever one you like, which is the pH is equal to the pKa plus the log of the conjugate base over the acid. And the pKa value is equal to minus the log of the Ka. So this is basically an equation that you could use in a common ion situation, which is really a buffer situation. And you do not have to use the ice table. And all you need is the concentrations of the base and the acid and the Ka value. So you can calculate the pKa value. Now, you should not use this in every situation. It's only for a very specific situation, which is a common ion in a buffer situation. You should not use it in every calculation, which is what people do. They go, cool, I got this equation. And I got two numbers, so seems like a great move. I'm just going to toss everything into that equation, hope for the best. You're just going to get an X, so do not do that. So it has to be specifically a common ion, which is buffer type problem. Otherwise, you should leave this on the sideline and not use it. The other good news is if you're unsure if it's a situation where you should use it, which hopefully you won't be, but in case you are, you could always do an ice table. So regardless, you could always roll with the ice table. You could use the Henderson Hasselbalch if you can know that it is the right situation to do it. They both should come out the same. This is the Henderson Hasselbalch equation that we use pretty much for any situation, if it's acidic, basic, or neutral. There is also a version of this equation that is sometimes used for basic situations. And I put it up here, but I would still highly recommend you roll with these equations here. And I'll tell you why in just a second. But much like pH, there's also our friend POH, yes. And you can tell the POH of a solution by taking the pKb plus the log of the acid over the base. So it's a little reverse if you go this way. The pKb, by the way, is equal to minus the log of the Kb value. B value. So some people will use that equation if it's sort of a basic situation, which frankly, in most cases, I feel is unnecessary because most questions are going to ask you what's the pH of the solution. So most of the time you're interested really in the pH of the solution. And since you could use this guy for acidic, basic, or neutral conditions, you might as well just go into there and get the right answer. Otherwise, if I use the other equation that I just wrote there, after I get the answer, I probably need to also subtract 14, right, to get it into the pH, right? So sometimes people forget that part and they run into some trouble. But there is a benefit as well that there is a relationship between the pKa value and the pKb value. So if you take the pKa value and the pKb value and you add them together, you get our lucky number 14. Yeah. So sometimes this is helpful in case you could only find perhaps a Kb value for something. You could calculate the pKb, subtract 14, and now you have the pKa value that you could go into the Henderson Hasselbalch equation with, or vice versa. So that's also a very useful one. So all these are useful equations, but again, I would probably keep your focus more so on kind of using those equations there for any situation. You'll probably be in good shape. Any questions on that there? So how can we use this? Well, let's take a look at the one we just did, which is 0.2 molar acetic acid and 0.3 molar sodium acetate. And we had our Ka value for acetic acid, 1.8 times 10 to the minus 5. So as soon as you could look at both of these things and recognize that they are related to each other, they're in common with each other. There are some common ions happening here. What is the relationship between these two things? It is the basic Bronsted-Lowry definition. There should only really be a difference of an H+. The sodium there is a spectator ion. It's not doing much. So if you get rid of the sodium, basically the only difference between those two things is one H+ in this case. And that means you could go right into your Henderson Hasselbalch equation. We could calculate our pKa by taking minus the log of the Ka value, which in this case is minus the log 1.8 times 10 to the minus 5. That is a 4.74 pKa value. We could then put this into our equation here, 4.74 plus the log. Which one is the base? Yeah, the acetate here is the base, as this is called acetic acid. So that should be the acid, yes. So let's not overlook that. So we should go with 0.3 up on top and 0.2 on the bottom. That is also something that gives people a hard time to figure out which one is the acid and which one is the base. In general, if you're comparing things that maybe it's unclear, the acid does what? An acid will donate a H+, which means typically speaking, the acid should have one more H+ than the other guy. Yeah. So that is how you know perhaps which one's the acid, other than that's acetic acid. So that makes sense, hopefully. So doing the math here, we're going to take a 0.3 divided by 0.2. We're going to take a log of it. We're going to add a 474 to it. We're going to get a wonderful number of 4.92, which, if I am not mistaken, is the same number we got when we did the ice table approach. Yes. So this demonstrates, again, as I was saying before, if you understand that it is a situation like this where you can use the Henderson Hasselbalch, it can save you some time by going into the Henderson Hasselbalch equation. If you're unsure or not, or don't want to use the Henderson Hasselbalch equation, you could still roll with the ice table. The important part, though, if you decide not to use Henderson Hasselbalch, but decide to do the ice table aspect of it, is what we talked about before, and where people make many times the mistake. You have to have somebody over here to make it a common ion type thing. Otherwise, you will get the wrong answer. So that is the only cautionary note I would say to people that stick with the ice table, which is perfectly fine. You got to make sure you got somebody on the right-hand side in this situation to do a common ion. Otherwise, you will get the wrong answer. Again, people sometimes go on autopilot, even in these type of problems, and they zero out the right-hand side, and they end up doing a weak acid problem when they should be doing a common ion or buffer type problem. Question on that there. Yeah. So Henderson Hasselbalch really specifically for buffers, and I've been alluding to it, which are common ions. So let us not talk about that yet. Let us do one more example before we talk about that, and then we will talk about the world of buffer. That is formic acid, maybe. That is potassium formate. Thank you for agreeing with me. All right, so I got a Ka value, which means one of them should be an acid, a weak acid, right? The one that's the acid here is which one? It is the guy with the extra hydrogen there, right? So that is this guy right here, which would be formic acid. So that would be our weak acid. This is a salt, really. And if you take that salt and you break it apart, you get a little formate here, right? And some potassium. Potassium is really just a spectator ion. So if you're not sure, you could cross out the potassium or the sodium that might be there, or any of those type of guys. And now you could hopefully see that this guy and this guy are pretty much related to each other. Yes, and they're related to each other by a difference of an H plus. Yeah, so that is how we could recognize that these things are related to each other. That is definitely a common ion since they are related to each other. And as we'll see shortly, that's a buffer basically we're looking at right there. And that means that we can use our Henderson Hasselbalch equation in this situation. We also can use an ice table if you wanted to. And since it is the acid that will be the one that would set up the equilibrium, if you chose the ice table approach here, it would look something like this. Initially, this would be 0.3. This would be 0. And again, most importantly here, you would need this number over here as a starting amount here, as basically what we have happening is we have this acid in the solution there. And now we're adding more of this guy in, right? And so we're increasing that amount. So we are going to have an initial amount of that really beefed up by us throwing in the other guy in there with it, right? We don't have to wait for it to kind of break apart and get some of it there. We're going to add the formate in to begin with. So now we have definitely an initial concentration that is there. The rest of the ice table here would be normal minus X plus X plus X. You've got your 0.3 minus X, your X, 0.52 plus X. Any questions on if you chose the ice table way, what it would look like? I'm not going to finish the ice table way, but at this point, obviously, you would use your Ka expression. You would maybe make an assumption that X is equal to 0 and make sure you check it. And that will get your X value, which will equal the H plus concentration, right? Which then could go into the pH equation. So a little bit of work there. I'm going to go Henderson Hasselbalch because, you know, we all like David Hasselhoff or whatever it may be there. I don't know. So pKa plus the log of the base over the acid. So obviously in this case, we got first calculate the pKa value minus the log of the Ka that was given to us 1.7 times 10 to the minus 4. And that's going to get us minus log 1.7 to the minus 4. Looks like a 377, it looks like. Now that we have that, that's going to be 3.77 plus the log of our base, which once again is going to be the guy with the spectator ion, 0.52 divided by our acid. And that's going to give us 0.52 divided by 0.3, a little log action, plus a 377. I'll go with a 401. Why not? In this case, you obviously should get to basically the same answer if you took the ice table approach. Any questions on that way there? All right, we will lay it up there for today.